Okay, you can sure it works. All right, hi. My name is Josue Torres Fonseca. I come from Boise State University. We're working with my colleagues, Dr. Casey Pennington and Catherine Henry, on a project titled Symbol and Communicated Grounding through Object Permanence with a Mobile Robot. So to define communicative and symbol grounding, communicated grounding is essentially the process of meeting what words mean in a dialogue. Essentially, it's a ability to form common ground between people communicating so that you have limited communication barriers while talking to other people. Symbol grounding is the idea of connecting the perceptual physical world to language in itself, or attaching a label to an actual physical object. So it has been established that symbol grounding is a side effect of communicative grounding. To go more into this, we can go into an example of a father teaching a baby about a ball that's currently in his hand. So the father might say that's a ball, and the baby with a ball in his hand doing whatever it wants to do with it and physically being able to play with it can repeat ball, and the father can say ball very good. Now, communicated grounding obviously happens through the idea that the baby now understands what a ball is, and they have common ground about what a ball actually is. So to talk about a ball in the future, they will have no limitation barriers, or at least limited communication barriers about the balls. Symbol grounding happened within the child in that the case that now it knows that the word ball is attached to the physical object in its actual hand right here, and that hopefully when it talks and plays with other balls, it will know that ball is attached to these other physical objects over here as well. Now, I want to go a little bit into object permanence. So object permanence is the ability to form and recall mental representations of objects, even when they are not in view. Now, essentially, PAJ identified that object permanence is happened in the sensory motor stage, which is a stage where children largely interact with the physical world while they're learning language. Now, this is important because to me, this suggests that object permanence is important for symbol and communicative grounding. So symbol grounding, usually most of the time, if I'm talking about an object such as a ball in the previous example, it won't physically be in my view. So if I wanted to actually attach that to a physical representation of an object, instead, I would attach that to the mental representation of the ball in my mind. It's also important for communicative grounding. Because I'm talking about a certain ball, such as a basketball from, let's say, the Celtics team, then I'm talking about the certain ball with my friends. I can't talk about that ball without it being physically in my view, unless I have object permanence. So I have a mental representation of that object in my mind. So if it seems to me that object permanence is important for communicative and symbol grounding, I wanted to do more research into this. So my actual research question is, does object permanence matter for communicative grounding and symbol grounding in an automated spoken dialogue system? So there has been background work gone into this. So the background work that I have seen is that essentially we have seen that object permanence is important for learning relational words and for searching behavior, which makes sense because we can't understand that something is behind something or understand that you can search for something without understanding, even though it's not in your view, it still exists in your universe. Now, other people have created spoken dialogue systems that have some understanding of object permanence, where Platinum have created a spoken dialogue system able to create a 3D model of a physical block world and answer spatial questions about it, or relational questions. And we already applied from the first citation that relational words it's important to only learn that if you have an understanding of object permanence. Now, people haven't looked into how communicative or how object permanence affects symbol and communicative grounding, but other people have looked into how collaborative efforts have affected communicative and symbol grounding as well as other things as well. So before we go into it, I have an embodied spoken dialogue system. So the robot I use for this dialogue system is Cosmo. We used it for a few reasons. One of the main reasons we use Cosmo is because for previous research my lab has done, we have seen that people perceive Cosmo as about a 2 or 3-year-old learning language child, which is important so that when they're teaching Cosmo language, they know that they have to teach Cosmo language. It's not like a teenager or an adult who just knows language overall. They have to treat it as a child and start teaching them about these objects in front of it or about anything related to language. We also use it due to its abilities. It has a head with an OLED display for eyes, so it can have some kind of version of nonverbal communication. It has a camera it can use for object detection, and it also has a speech synthesizer who can speak to the participant and have some feedback. We also have something called SLAM, or simultaneous localization and mapping, which we use for our approximation of object permanence. I'll go into this in a bit. So this is our whole system. I'll go into it bit by bit. But the two main things I want to highlight right now is that we use an incremental framework, so it processes things word by word, such as humans do. And we also extended it for multimodal use using Cosmo. So essentially, it's an embodied spoken dialogue system that is put within Cosmo itself, so that can interact with the physical world and learn language as it relates to the physical world around it in itself. So going into it, so for object detection, we use YOLO. We apply this as a means for object classification and drawing bounding blocks around objects. So essentially, that drawing bounding block around the objects, it just helps reduce noise, and we send that sub-image of that bounding blocks to Clip. Now, I'm heard many of you have heard Clip. We don't use it in the traditional sense that Clip is usually used for. We use Clip's image encoder, setting the bounding blocks and the sub-image within that bounding blocks to Clip to vectorize it to a feature vector of size 512. Now, looking more into the bounding box itself, that bounding box is first off sent to SLAM, which is a way of approximating object permanence. So that bounding box has dimensions to it. And with those dimensions, we can get those dimensions and use that to create some kind of 3D rectangular prism, as you see in frame 2 right here. And essentially what happens is that in 1, we draw a bounding box around the actual base itself. And then those dimensions are sent to create the rectangular prism. So now it remembers where the object actually is. And importantly, we attach an ID to that actual object, custom object in Cosmos local map. And we also have the coordinates there. So if it sees the object again, it's no longer a new object to it. It knows it's an object as seen before. And the way it works is through the quadtree map. I'm going to go into a little bit of detail. If you want to hear more, you can look in the paper. But essentially, the big part of it is that we have a parent, which essentially is the whole square itself, which is the square of Cosmos actual local environment map. And it has 4 children, which is the quadrants of that square. And we recursively go down this until you get to the leaf nodes, which is every single individual square, which you can see in the frames either 1 or 2, where you have the small squares, is the leaf nodes. Now, if the parent node is black, that means all of its children have some kind of object in one of those quadrants it's looking at. If it's gray, that means some of its children have an object in them. And if it's white, that means none of its children have objects in them. It's just an efficient way to be able to do this. But the important thing to notice here is that we have an ID attached to coordinates, and it can remember the location of objects using the bounding box information. They go more into grounding semantics. So we use the word classifier module. And essentially what it allows us to do is allows it to perform symbol grounding. Essentially, it can attach a word, such as in the previous example, the word vase, to an image vector representation of an object. And it showed positive examples of the vase, which is the vase it's looking at, and also negative examples, which would basically be previous objects that I've seen before that aren't a vase. It basically gives it a better idea of what makes a vase a vase. Within this word classifier module, we essentially also have the coordinates of the object itself. So the word vase is not only attached to the feature vector representation of the vase it's looking at in the image, it's attached to the coordinates of the object itself. So if it asks where the object is, it can go to it directly without too many issues. Now, for dialect act recognition, essentially what we did is we used the Google Speech to Text API for word level transcription. And this transcription is sent to Rasa, which helps us get and gather the dialogue act or intent of the user. We have 5 different dialogue acts. We have the positive user feedback and the negative user feedback to let us know if Cosmo got a question correct or incorrect. We have the where questions and what questions, which essentially allows us to quiz Cosmo to know if it's actually learning about these objects correctly. And then we have statements, which essentially whatever a statement is said, which is not any particular dialogue acts I said above, it just basically means that Cosmo is being taught about these objects in front of it, so it should start learning. With these dialogue acts, we use this to change the state Cosmo is in. The default state of Cosmo is the explorer state. Well, essentially all it does is it randomly explores objects that is in front of it, and it just tries to learn about these objects. But it only starts learning once participants utters a word, such as this is a vase. When it learns about that, it uses the word classifier module to learn what a vase is, whatever object currently in front of it is. And once it's done learning, it goes back into the explorer state. Now, from the explorer state, assuming it has learned everything or learned enough, they can start quizzing Cosmo and they can ask it, where is the vase or where is some other object? And you can use the SLAM module to find it, or without SLAM, it has to randomly look at objects until it sees what it looks like is a vase or is in itself. If it finds it, it will answer saying this is a vase, or I believe this is a vase essentially. If it doesn't answer, it can't find it, it'll go back into the explorer state. In the answer state, essentially it can ask when in front of an object, what is this object? If they answer correctly, it will just say the object it is, and then it'll go back into the explorer state. So as you see, the dialog acts essentially used to be able to change the state we're in, and the default state is the explorer state. Now the whole system overview is this right here. Essentially going into one more time, we have the camera. If we're looking at the vase, it will draw a bounding box around the object using the object detection module. And the bounding box we sent both to Clip and to the SLAM module. In Clip, we vectorize the image into some feature vector representation, which is sent to WAC. With SLAM, we use that bounding box to create a representation of the coordinates of the object in Cosmos virtual space and map that you can use. And that's also sent to WAC. And when a participant utters something, such as this is the vase, the word vase is sent to WAC to not only attach the word vase to the image of the object itself and the feature vector representation of it, but also attach it to the coordinates of the object. And then the NOU or Rasa essentially used to just change the state of what Cosmos is in, if it's learning or if it's exploiting the knowledge it already has. Now, finally, our experiment is that we have participants teach Cosmos as many words as possible about the objects in front of it in this image to the bottom right. And they are periodically quizzing Cosmos to make sure it's actually learning something. We have an A/B test where we spend 20 minutes with Cosmo, with Object Permanence, and 20 minutes without Object Permanence overall. Now, with Object Permanence, when it's finding an object, essentially it can look at the word vase and find the coordinates and go to the object directly. Without Object Permanence, if it doesn't have Object Permanence, essentially when it's finding something, it randomly looks at these objects until it finds what looks like a vase overall. The reason we did this is essentially we wanted to know that does Object Permanence actually have an effect on symbol communicated grounding? when we have object permanence than if we have it without it. Now, after each interaction, we have Cosmo or the participant fill out a survey measuring communicative grounding using the Godspeed questionnaire. And then we have 24 participants gathered, 18 of them male and 6 of them female. As you see here, there's boxes around every single object in front of them. The reason we did this, we constrained Cosmo to only be able to go at these boxes. So technically it knows that there are objects there, it doesn't know that what the objects actually are. And even though it knows that there are objects there, it still specifically has to learn where the objects actually are in itself. And the reason we did this, the limitation of the technology, is that if Cosmo fell off the table or hit the wall, it would delocalize its map and wouldn't be able to remember where things actually had. Now, the metrics we used is for symbol grounding, the experimenter I kept track of the number of utterances, positive and negative feedback, and the number of questions asked. The participant kept track of the number of correct answers to measure accuracy. For communicative grounding, we had them fill out the Godspeed questionnaire, which has a Likert scale from 1 to 5. Well, 1 is negative information, and 5 is more positive kind of view. And we also added additional questions about responsiveness and intelligence of Cosmo. So our overall results are basically here. So the baseline without object permanence, the number of words that Cosmo has heard or told is 15.9. The mean of the questions asked is 10.7, and the percent correct is 70%. With object permanence, the heard words is 18.8. The questions asked is 20.0, and the percent correct is 82.7. So it seems to be that with object permanence, Cosmo is better at forming symbol grounding and more accurate overall. But also communicative grounding seems to be better and that the participant is more engaged. As not only do they teach Cosmo more words, they ask it more questions, they're more curious to know the abilities of Cosmo and want to work with it more. Now, going more into the perception of Cosmo overall. So we had them fill out the Likert scale and we measured intelligence. Now, intelligence with SLAM or object permanence, the mean is 3.67 and without a 3.21. And responsiveness, how quickly you can answer a question, the mean is 3.96, and without, the mean is 3.50, which makes sense because the faster you can answer a question, the more intelligent Cosmo would seem to be overall. But how does this affect what they think about Cosmo and how engaged they are with Cosmo? Well, looking at this, with object permanence, or with SLAM, I call it, the mean is 4.62, and without it is 3.92. And then this, with a higher interest, it also affects how much more they want to spend time with it. They want to spend more time with object permanence with SLAM with a mean of 4.33, and a mean without SLAM, which is 3.775. This is important overall because the more engaged they are with it, the more Cosmo will learn. If they weren't engaged with it after all, and they don't start teaching it more about Cosmo and what if the objects in front of it actually are, then it will learn less overall. So higher engagement is definitely a really good thing. Now, essentially, it's clear that object permanence perceived to positively affects Cosmo's ability to learn language. We have approximately 13% more accuracy with object permanence than without. And overall, the mean values for reading related to perception were higher for object permanence than without object permanence. Where Cosmo's age was actually estimated to be 3.5 years of age with the test condition of object permanence and 2.6 without, which shows that it seems to be more intelligent or perceived to be more intelligent, but it's not too intelligent. It's not like a teenager or an adult that has a complicated vocabulary that it knows. It's just smart enough to know that it's learning better overall. In conclusion, basically what we have is we conducted an experiment with 24 participants working with Cosmo and performed the language acquisition task both with and without object permanence. And understanding of object permanence resulted in improved communication and symbol grounding, as seen from the stronger engagement and the higher percentage of correct answers or higher accuracy. And essentially, the user perception or engagement with object permanence and without was better with object permanence. Our findings essentially suggest that object permanence is a necessary component of any spoken dialogue system. If you want to make a spoken dialogue system that can mimic the abilities of humans and that actually can seem like it knows what they're doing, then it has to have the ability of object permanence to remember where objects are and to respond quicker and seem more intelligent. Our future work involves designing the same spoken dialogue system for other robotic platforms, but also I want to look into how object permanence can help examine other people's perspective. Essentially, what I mean by this is that if I ask something such as, I want the cup to my right, can we use object permanence to have her imagine the other person's perspective and they say to their right, what do they mean by their right in itself overall? Thank you for coming to my talk, and do you have any questions?
Any questions? And it would be appreciated if you can state your name before asking questions. That's great. Thanks.
Hello, my name is Gabriel. Thank you for your presentation. Very interesting. I wonder how you think this object detection will scale. I mean, if you do that in this kind of bottom-up manner, I mean, if you have a share, it might be a share, but each leg could be an object also, and sort of there are a lot of potential objects in the world around you. Would this model work if you sort of find objects on all kind of levels and objects within objects and so on?
So are you saying or asking how well this, like we're a classifier in the like attaching words to objects works if we have more than one object in view?
Yeah, when you have a more complex scenario where with complex objects consisting of
Yeah,
lot of-
so actually we did look a little bit into that. And essentially, if you look back at Cosmo right here in the image we have, sorry, it's kind of annoying. The vase is kind of in view by itself all the time. We only look at one object at a time, mostly because Cosmo with its camera is very small. So we can only really look at one object at a time. We did try to have it look at more than one object at a time. The issue is that Cosmo's camera has pretty low quality. So it could really not accurately get to more than one object in itself. And if it really tried to do that, then essentially it wouldn't work too well. But we justified that mostly because that when a child is learning about an object, usually they don't learn about a bunch of objects in front of it immediately. The parent has them focus on one object and maybe give them that object overall. So if they're learning about a ball, we'll give them the ball and have them learn about it while they're being able to interact with it. So yes, it won't work very well with seeing more than one object, but it's essentially how children will learn as well. They can't learn very well if they have a bunch of objects in front of them and you say, this is a ball. They'd be like, what ball are you talking about? That, any question?
I'm Matthew March from the Army Research Lab. Really interesting talk. I think a great area to study. So I wanted to ask you about the 13% accuracy improvement from using the object permanence.
Okay.
So did you do an error analysis here to see what's getting better with object permanence? Like some examples of dialogue exchanges where you see, maybe a comparison without it and with the permanence that you're seeing a clear improvement, for example?
We kind of did a little bit of that. Essentially what I saw is we did have a kind of different things. Actually, if you look at the objects itself, you'll see that some of them have kind of similar characteristics, such as the base both being blue and some of them having similar colors of shape overall. We did that on purpose so that if they ask something such as where is like the blue or where is a blue object, it can go to it. In this case, what we had it do is essentially if it went to a blue object, that seemed to be right, then we kind of that's correct, but it couldn't go to a specific blue object overall. But usually it got questioned incorrect if it was kind of ambiguous about what an object actually was itself, because then sometimes it'd be like, well, there's multiple blue ones and I would guess something completely wrong overall. I don't know what you're talking about, and stuff like that. But also it was kind of more tricky when you kind of taught it more. Once it learned more about this object, there are 7 different objects in its history, it could still accurately do it, but sometimes like the first object we asked it about it would most of the time get it right, but sometimes get it wrong. So the issue is like the history, but also with ambiguity of what you're actually talking about overall. But I mean, it seemed to be 13% more correct, mostly because it could remember the objects itself and be able to go to them directly. It was just the issues with ambiguity in history that mostly caused the other, like what, 17% to be wrong.
Sorry about that, because for some minutes we need to go further. And thanks a lot for the interesting talk.
Thank you.
From news about towards